Hello, my differential equation class student. This is last section. What we covered in this class is 3.3. Here is, I think it's last. But we see what happened. Okay, today we talk about regular singular point and solution around regular singular point. First, we need some definition. Let's go, we have some equation. We rewrite this equation in standard form. This means first coefficient is, oh, I'm sorry. Equals 0. And we can rewrite this equation form when we can big px rewrite like small px divide by x y prime, and big qx like small qx divide by x square y equals 0. And here we have this kind of definition. Singular point x equals 0 is we call regular singular point, or singular regular. No, better is regular singular point if our new function small px and qx are both analytic at x equals 0. Otherwise, this point called irregular singular point. This means if not, point called irregular singular point. Okay, see some example. Example 1. If you have x squared 1 plus x second derivative plus x times 4 minus x squared first derivative plus 2 plus 3x y equals 0, I can rewrite this equation as part plus, okay, 4 minus x squared, x cancel it. This means here I have only x1 plus x. This is my first derivative plus 2 plus 3x over x squared 1 plus x. This means this is my px and qx. Okay, I'm right. Big px, it will be 4 minus x squared x 1 plus x, and big qx, it will be 2 plus 3x over x squared 1 plus x. Well, you can easily see for both of this function both of this function is not analytic at x equals 0. This means x equals 0 is singular point. But what is will be small function px? It will be 4 minus x squared over 1 plus x. What is small qx is 2 plus 3x over 1 plus x. Both of this function analytic at x equals 0, and this means x equals 0 is regular singular point. Singular point. We can one more example. Example 2. Let's go our function x squared second derivative plus x squared sine x. When I write here not correctly. It's not x squared, it's x to the fourth. X squared sine x y to the prime plus 1 minus cosine x y equals 0. Write it like standard form. You have second derivative plus sine x over x squared plus y prime, I forgot, 1 minus cosine x over x to the fourth y equals 0. Remember definition p and q. We have p, small px, I write only here, it will be sine x over x, and small qx, it will be 1 minus cosine x over x squared. Okay, checking analytic or not, we remember series. We remember what kind of Taylor series we have for sine and cosine x, and we rewrite. Okay, px will be 1 over x sine x give us x minus x cubed over 3 factorial. We did this trick before, we can check in different lecture. X7 to the 7 factorial and continue. Distribute, you have 1 minus x squared over 3 factorial plus x to the fourth over 5 factorial minus x to the 6 over 7 factorial and continue. This is analytic function. What about qx? Q to the x, it will be 1 over x squared. Here you have 1 and subtract Maclaurin series for cosine x, who is 1 minus x squared over 2 factorial plus x fourth over 4 factorial minus x6 over 6 factorial and continue how long you want. If you distribute inside, open parentheses, you have 1 over x squared times x squared over 2 factorial minus x to the fourth over 4 factorial. I move a little bit. Minus, no, now it's plus x to the 6 over 6 factorial. And doing same trick, this means distribute, you have 1 over 2 factorial, I think is 1/2, minus x squared over 4 factorial plus x fourth over 6 factorial. It's over 6 over 8 factorial and continue. This means this function is still analytic function and x equal 0 is a regular singular point. Singular point. And now we can study method of Frobenius, who help us found solution around regular singular point. what we interested here? Usually something interesting happened around that point. We cannot use all singular point, but some of them, singular, a regular singular point, we can use. Okay, what is work? How work this method? For example, I have some equation with constant variable. No, not all constant. I write and then you can see what I mean. I have x squared y second plus p0x y to the first and plus q0 y equals 0. This means p0 and q0 is some constant. Okay. If I pretend x to the power, and if I'm solving this kind of equation, just a moment, we can easily check first. X equals 0 is a regular singular point. And if I rewrite this kind of equation, r minus 1 plus p0r and plus q0 equals 0, and r is solution my equation, the solution this quadratic equation, second one. This means we have y equal x, y depend x some function. It will be x to the power r multiplied by cn x to the power n, and start with 0 to infinity, or if we put inside cn x n plus r, whereas n start with 0 to infinity, it will be solution our differential equation. Okay, great. It's work if you have some special equation, but what happened if you have some function there? This means we have some equation this shape, x squared y second plus x p to the depend x y first plus qx to the y equals 0. And let's go px, we can rewrite, use Maclaurin series like p0 plus p to the n x plus p to the second x squared. You see, I'm not counting what coefficient there, divide by some factorial. I'm only can any good enough function rewrite like this kind of series. And continue. And qx, it will be q0 plus q to the first x plus q to the second x squared plus and continue. If we found our solution our equation for like this kind of power series, it means our r need be solution quadratic equation q0 equals 0. Looking here, this means if you have p and q not constant but function, you can use value your function in 0 point and build your equation. Okay. Now we found exponents, if it's possible, for Frobenius series solution of the equation. Okay, write our equation. It will be 2x squared 1 plus x. This means I'm doing some example. Y second plus 3x 1 plus x to the cube y prime and minus 1 minus x squared 1 minus x squared y equals 0. Okay, write a standard form, and we can see y second derivative, it will be plus what we have. It will be, just a moment, I think here I make it some mistake when I write 1 plus x all this cube, not 1 plus x cube. Okay, it's no big deal. What we have here, 3x 1 plus x cube divided by 2x squared 1 plus x. This means we cancel it here and cancel it there. I especially write this different color when you can see what I did. Okay. Minus 1 minus x squared, I'm rewrite like 1 minus x 1 plus x, and then divide by 2x squared 1 plus x. Here is y, here is y, equals 0. And what is cancelled here? 1 plus x, 1 plus x. Okay, now, oops, we are ready for write second derivative. It will be 3/2 1 plus x squared, all of them over x. Oh, I forgot about first minus 1/2 1 minus x over x squared y equals 0. This means our Q0, it will be 3/2, and our, just a moment, I mixed up, our P0 is equal 3/2. How I did this one. Our P0 and our Q0 equal -1/2. Okay, because this one will be P to the x, here will be Q to the x, no, and it's minus. Okay, and now we have this kind of quadratic equation, r times r minus 1 plus 3/2 r minus 1/2 equals 0. R squared minus r plus 3/2 r and 1/2 equals 0. R squared plus 1/2 r minus 1/2 equals 0. This means here we have r plus 1, r minus 1/2 equals 0, and we have two solutions, r equal -1, r equal 1/2. This means you have first solution, it will be x to the power 1/2 series cn x to the power n from 0 to infinity, and second solution is will be x to the power -1. Oh, practically is different coefficient you have. Maybe it will be better if we first one write is like an, and second one is bn x to the power n, and from 0 to infinity. Great. And how use this method? We study one more very big and very important theorem. We tell us theorem number 1 for today. Let's go as x equals 0, regular singular point. Singular. Equation, for example, x squared y second plus x px y prime plus qx y equals 0. This is our equation 1. You know, any equation, any quadratic equations, any differential equation second order, you can rewrite this shape. Okay. Let's go row. We define like minimum of radius convergency, minimum radius convergency, series for our function px. This means sum p to the n x power n, and from 0 to infinity, and qx. Let's R1 and R2 roots I mean real roots, this means real numbers. Our equation are r minus 1 plus p0r and plus q0 equals 0, and we plug r first greater than r second. If you have two numbers, usually is greater or equal r second. Okay. Then first, for any positive x, exists solution equation 1 of the form first x equal x to the power r1 a n x to the n power and from 0 to infinity, whereas a is 0, non-zero. Second, if difference between numbers r1 and r2 not equal positive integer, integer, believe me, here is r, or 0, then exist linear independent solution, linear independent solution. Second, by second, with x to the r second, bn x to the power n, and from 0 to infinity. And radius convergency, these two series, is at least r. radius. This is very important, this being for what x your solution is work. Okay, now I think it's done for first part, and part number 2 for this section will be part about how we're solving our equation.